All right, a lot going on in this question, though we're not given a ton of information. We got to solve for basically what's in this tank. We have a 7-liter tank. It's at a little over room temperature, 25 Celsius, 25.5 Celsius, and 4.32 grams of chlorine pentafluoride and 6.84 grams of dinitrogen monoxide. And so we got to do first solve for mole fraction. So the way we do that is solve for number of moles. And we can do that using the molar mass of each of these. Then we will use that number of moles again in solving for the pressure using our rearranged ideal gas law. Now we'll do it for each one, and then we can actually add up those two pressures because of Dalton's law to get our total pressure, which is the last question. Notice it's in atmospheres. One thing to know is this is actually 3 degrees or 3 significant figures. Sometimes it's given a 2 significant figures, so maybe it's 8.1. And when we're doing addition, now remember 273.15 is our what we're adding to go to Kelvin, and then it's based off here, right? So we would go 2 and then 281.25. So this would actually be 281.3. And it would be 4 significant digits. So remember, with addition and subtraction, we can actually gain or lose significant figures. So even if this is only listed as 2, it actually becomes irrelevant because it goes up to 4. And so then sig figs would be based on some of these other ones. So big, something to be aware of as you're working through this problem. If you have one that's given where there's only 2 sig figs on temperature. Okay, but let's first start out with mole fraction. So I'm going to start out with my chlorine pentafluoride, so 4.32 grams. And this has, I looked it up, has 130.45 grams per 1 mole. And so 4.32, we get 0.03312 moles. Now we have 6.84 grams. This is 44.01. So 0.1554 moles. Okay, so we total those up. And we get 0.1885. And then if we divide each, we get the mole fraction. And it's not percentage, so 0.03312 divided by 0.1. We get point, so for the ClF5, we get 0.1757. And for the N2O, we get 0.8244. Now that's 3 significant digits, so I'm going to go and plug these in as 0.176 and 0.824. Okay, there's part 1. Now we're going to keep track of our moles. And so we're going to rearrange. So our PV equals nRT. We're going to solve for P. So we're going to divide by volume. So we get our first moles is 0.03312. Now we're going to multiply by Now we do need to do our Kelvin. So we have 273.15 plus 25.5. And I'm just going to keep all the digits right now. And then we divide by our 7 liters. Okay, our other pressure is moles. Everything else should be the same. And we'll get our 2 calculations. So 0.03312 times 0.08 times 298.65. So I get 0.1160 atmospheres and 0.5443 atmospheres. Now, if I total those up, .6603. Now we're going to go with our 3 sig figs. When I type these in, so we'll go with 0.116, 0.544, 0.660. Dalton's law tells us that partial pressures add up to the total pressure. Okay, there we go. So be careful with significant figures. And then there's a lot going on. So start with mole fraction, then pull partial pressure using the ideal gas law. You could also solve for this total pressure if you added up the 2 moles like we did in mole fraction and did 1 more P equals nRT over V. But we can also just add them.